In this example, we have a projectile. So we have a projectile that's a ball, as shown in the figure. The initial velocity of the ball is 30 meters per second, and it's thrown at an angle of 40 degrees above the horizontal. Find the maximum height, h, the time it takes for the particle to reach point C, and the total horizontal range, L, that the particle travels. All right, so we have a ball. It's thrown up at a particular velocity and angle. It hits its apex, and then it comes down below where it starts. All right, a lot of times when you do projectile problems, you label it and you put a coordinate axis. Well, this figure already has that. Has a label of A at the beginning, C at the end, and B at the apex. And we have the X direction and the Y direction. All right, so how are we going to attack this problem? We're going to start with the X direction. I always like to do this in projectile problems. It's the easiest. You can often find missing information right away or save that equation for later. And then we'll analyze the Y direction. All right, so the X direction, we have this range equation, or the position in the X. Remember that the X velocity is constant. We're going to apply this equation at point C. So the distance, point C, is L. The time it takes to get to point C is TC. And the X velocity is V naught cosine theta. All right, we can't solve for anything now, so we're going to label that equation 2 and go on to the Y direction. In the Y direction, we have 3 equations that we can choose from. We have the velocity equation, the position equation, and then the equation that's derived from the AdS VdV equation. So we need to choose which equation is going to be the easiest for us to use. So what I usually do is look at each equation and what point that I might apply it at. So if we look at the velocity equation, we could apply it at C, but we have no idea what the velocity at C would be. But if we apply it at B, we know the Y velocity at B is 0 because it's the apex. So this one might be a good equation to apply at point B. For the position equation, we don't really know the position of B, but we do know the position of C. It's minus 10 meters. So that equation might be a good one to apply at C. All right, well, if you go to the last equation, what point could we apply that one at? Well, we know the velocity of B in the Y direction, and also it has position, right? So that would give us H, whereas the velocity equation would give us a time. We could use that, and then we could use the time in this equation to get the position. But if we start right away with this third equation, it will give us position without having to find time. All right, so let's move on. So let's use that third equation, and that will give us the height. So we apply that at point B. So the height at point B is h. Initially, y is 0, because that's where we placed our coordinate system. And then we have the y initial velocity and the velocity at B, which is 0, because it's the apex. So we can solve for h directly. Again, we could have used the velocity equation, found time, and then plugged time into the position equation. But this one was faster. All right, so now let's determine which equation we should use at C. So we use this third equation to find the position at B, but what should we do to find the time it takes to reach C? Well, we need an equation that has time in it, and we do know the position. So let's go ahead and use this equation and apply that at point C. All right, so if we apply it at point C, the position in the y is minus 10. It starts out at 0. We have the initial y velocity, time that it takes to get to C, and so on. So we can solve for the time at C, plug this back into equation 1, which we got from the x direction, and we get the range.